got his doctoral fellowship at the Department of Physics and Astronomy in the University of Bologna with Professor Francesco Ferraro as a supervisor. After he spent some PhD fellowship in different institutions, including the University of Bologna, University of Groningen, and Leuven, I think. And he has been working with Amina Helmi and providing a very important contribution in the field of stellar stream and astrometry for both field and star cluster. Let me say that despite of his relatively young age, he has a very outstanding academic record and is providing very important contribution to the field of the study of the formation of the Milky Way in these recent years. Since the July of this year, he is a staff member at the INAF National Institute of Astrophysics in Bologna. So please, Davide.
All right. So first of all, thank you very much for the invitation and for the very kind introduction, Santi. So indeed, today I would like to talk about the Milky Way assembly tale as told by its stars and globular clusters. And I would like to start the presentation with a question. That is, how did the galaxy become like what we see today, which is like this beautiful picture here in the background. So basically a galaxy made of several components, starting from the thin and the thick disk, the center of density, which is the bulge, everything embedded in the much sparser distribution that is the stellar halo. And well, to answer this question, the best way to go is to focus in on this latter component, the stellar halo. And the reason is the following. The reason is that according to the standard cosmological scenarios, the large galaxies that we see today, just like the Milky Way, have built up hierarchically, meaning via merger of smaller systems, as we can see in this sketchy image. And well, if we focus on this last time step of the simulation, you see that the debris of all of the merger events basically made up the stellar halo of the central galaxy. So if we further focus on the halo of the central galaxies, in this case, you can see that basically the color coding tells you the origin of each of these stellar streams. So stars color coded in different way have different progenitors. But if we were to eliminate the color coding and only base on the spatial information, we would not be able to tell anything about the origin of the stellar halo. So this is to say that we can't rely on the spatial information only, we must rely on other information, and we also have to pick carefully our tracers. Stars are particularly useful if we are nearby, but in places that are farther away from us or in regions that are very much dust extincted, maybe other tracers are better. And globular clusters, I think, provide a very good example of this. And you will see why I'm saying this later on with the presentation. But that said, what are the properties we have to rely on in order to try to reconstruct the assembly tail of the Milky Way? Well, the properties are those that did not change even after our tracers were accreted from their former hosting galaxies onto the Milky Way. And these are, for example, the age distribution, the chemistry, and their dynamics. And in this presentation, I will mostly focus on the dynamics, and the reason is the following. So if we were to look up at the stars located in this location, as I said, the spatial distribution wouldn't tell us much. But as you can see maybe from these arrows, all the stars that are here and that belongs to this stellar stream move coherently. So this means that in the velocity space, all of these stars with a coherent origin would look clustered together, and even more so in the integral of motion space. So the integral of motions are conserved quantities such as the orbital energy or the angular momentum that makes it easier to identify and reconstruct the debris of certain old progenitor, because the tracers belonging to this all remain clustered together in the integral of motion space. Now, in order to determine the integrals of motion, we need to determine the orbits of our tracers. And to do so, we need the 6 parameters of the phase space. Now, the 6 parameters are the following. 3 comes from the 3-dimensional position of our tracers. The fourth is the line of sight velocity, and the other two are the two components of the proper motions projected on the plane of the sky. So once we have the full phase space information, we can assume a certain shape for the gravitational potential, and we can integrate the orbits. Now, historically, the most difficult parameters to determine among these were the two components of the proper motions, but this is not anymore the case. And the reason is clearly the advent of the Gaia mission. So as you can see, Gaia in the latest early data release 3 was able to determine the proper motions for about 1.5 billion of stars. And to show you how good Gaia proper motions are, let's focus on globular clusters. So in this plot here, I am showing the precision on the absolute proper motions that we had for globular clusters before Gaia, and this is with Gaia. So the x-axis is logarithmic, and this basically means that we have gained 2 orders of magnitude in precision with Gaia. And this also means that Gaia basically beats HST. Now, the reason for this is that in order to determine the absolute proper motion, HST requires background galaxies, because background galaxies provide the absolute proper motion 0 point, because they are so far away that we know their true proper motion, which is 0. But on the other hand, Gaia directly measures absolute proper motions. And this is why we can basically get so precise proper motions for this stellar system, because the precision is increased by the number of stellar members. Now, that said, so we have the proper motion information for the sample of globular clusters. We can combine this with their line of sight velocities and positions. We can assume a shape for the gravitational potential, and we can get the orbits of this system. So here, in fact, you see portions of the orbits of the globular clusters in blue, and in red you can see portion of the orbit of another class of tracers that are the dwarf galaxy satellites of the Milky Way, which I will talk about in this presentation. But for now, let's focus on the orbital properties of globular clusters. Now, first of all, let's focus on this leftmost panel, where I show the apocenter versus the pericenter. Now, what I think is remarkable here is the fact that the different colors used to make this plot basically corresponds to 3 different assumptions on the gravitational potential. And this is to show that basically, of course, assuming a different shape for the gravitational potential leads to differences in the orbital properties. But mainly you can see these differences are not extreme. But I should say that this subsample of globular cluster is limited in apocenter. It goes up to 25 kpc. Of course, there are globular clusters farther away. For those, especially if they move on very eccentric orbits, the differences due to the assumption of the gravitational potential might be a bit large. But that said, let's move to this other plot, apocenter versus eccentricity, to show that the large number of globular clusters actually move on rather eccentric orbit, more eccentric than about 0.6. So please keep this number in mind, because I'll be back on this later on. And now let's move to the third plot, which is apocenter versus vertical angular momentum. Now, the apocenter basically goes as the energy. So this is basically the integral motion space for the globular cluster. This is why I think you will recognize this shape later on, where I will focus on the integral motions for the entire sample of globular clusters. And at this point, let's move to the other class of tracers, which are the dwarf spheroidal galaxies orbiting the Milky Way. Now, here you can see the projection of the orbits of these dwarf spheroidals in the XY, XZ, and YZ plane. And I think that here it is pretty remarkable, the similarity between the red and the orange orbit. Maybe you can see it here, but they are very similar in all of the 3 panels. Now, these 2 dwarf spheroidals are Draco and Ursa Minor. And the reason why I am saying this is that it is actually unknown how the assembly of a galaxy takes place. There are several hypotheses, and this might be the very first evidence supporting the so-called group infold hypothesis. So the galaxies are created by a central larger one in groups. But now let's move to the same plot that I showed before for the globular cluster. So apocenter versus eccentricity. Why? So the reason of this is that, based on what I said before, that large galaxies build up by creating smaller systems, we might expect that if these small systems are massive enough to host a system of globular clusters, then these globular clusters would then become part of the globular cluster system of the central galaxy, in this case of the Milky Way. So we might expect a dynamical link between the population of Milky Way globular clusters and the population of the Milky Way galaxy satellites. But by looking at this plot, there are no dwarf spheroidal galaxies orbiting on orbits that are more eccentric than that 0.6. So does this mean that this dynamical link doesn't exist? No, this is not the answer. The point is that the dwarf spheroidal galaxies that we can observe now are clearly a biased sample because we are not observing those that were created in the past and that are now completely dissolved within the Milky Way Halo. So here is where the assembly tale of the Milky Way begins, and I would like to start this tale with the main character, which is the Gaia Enceladus dwarf galaxy. So these are the steps that led to the discovery of Gaia Enceladus. So everything started from the KOLO magnitude diagram of the kinematically selected nearby halo. So as you can see here, this KOLO magnitude diagram seems to be split in two sequences that run almost parallel one respect to each other. And well, if we look at the chemical space for a subsample of these stars, you see that basically this bimodality seems to hold. Now, in this case in particular, I'm showing the alpha over iron versus metallicity plot. And you can clearly see that one sequence exists that remains alpha enhanced up to a metallicity of about minus 0.5, and then starts to drop towards solar values. And another sequence exists where such a knee point, the knee point is the point at which the alpha element starts to drop, is set at much lower metallicity. It's about minus 1.5. And it is very well known from chemical evolutionary models that the metallicity of the knee point tells information about the environment that formed the stars, mostly in terms of star formation rate. But for now, let's keep to this evidence that basically says that the nearby halo seems to be dominated by two components that might have different chemistry and maybe age, as we'll see later on. And then we added the dynamical information. So here you see the integral motion space, again, for the nearby halo. And you can see that the distribution of these stars clearly show three main features. The first is that despite we got rid of disk stars with our selection, which are these blue stars here, a rather prominent component of stars that move on thick disk-like orbit still exists. The second feature is that the distribution of the stars in this plot is clearly clumpy, but this is actually what is predicted for halos that are built via merger. And the third and most important feature is that this distribution is dominated by this blob of stars that you see here, which is slightly retrograde. Maybe you can see better this blob in this other plot here. Now, we looked at the distribution of blob stars in the velocity space, and we compared this with a simulation of a 5-to-1 mass ratio merger of a dwarf galaxy that was orbiting around a retrograde orbit inclined by 30 degrees with the Milky Way. And you can see that the similarity of these two plots is striking, not only in terms of the blob, but also in terms of this arch-like feature that you see here in both panels. Now, at this point, I should say that the same features was simultaneously discovered by Belokuro and collaborators, and they found out that this was made up of stars moving on very eccentric orbits, so the region of the eccentricity space that was lacking points. And because of the shape of these orbits, they called this feature the sausage, whereas we prefer to call it Gaia Enceladus. And at this point, we put everything together because we selected dynamically the blob. We looked at its distribution in the chemical space to find out that it populated entirely the low alpha sequence. But low alpha sequence means that the stars of the blob formed in an environment that formed in stars with a much lower star formation rate compared to Milky Way stars. This environment This environment was thus a dwarf radial galaxy that was accreted by the Milky Way long ago. So basically, the stars of the blob, the stars of Gaia Enceladus, populates the low alpha sequence in the chemical space, the blob in the dynamical space, and the blue sequence of the color magnitude diagram. Now, later on, Carme, Gallat, and collaborators, 2019, found out that the two sequences of the CMD actually shared very similar ages, so they were basically coeval. Now, the stars of the red sequence of the CMD populates the high alpha sequence of the chemical space, and that prominent feature that moves almost on disk-like orbits in the dynamical space. So the picture that we have is that basically long ago, Gaia Enceladus was accreted by the Milky Way. At that time, a disk was already in place, but because of the encounter, the stars of the disk were dynamically heated. So they basically puffed up, and their stars were pushed on orbits that looked like that of the thick disk, but that were more eccentric. So this is the overall picture about the accretion of Gaia Enceladus. Now, since then, many works try to reconstruct the most fundamental properties of Gaia Enceladus, which are the stellar mass and the accretion time. And I would say that there is good consensus on the stellar mass, which is of some 10 to the 8 solar masses, and on the accretion time, which is between 8 and 10 gig years ago. But be careful that at this time, the mass of the Milky Way was clearly smaller than the current one. So at this time, Gaia Enceladus was a rather major merger. The mass ratio was between 4 to 1 and 5 to 1, like. All right, but this is only the main character. Main character because of the mass, basically. It was one of the most significant merger events. But others were discovered thanks to Gaia. Another one is the progenitor of the Hermes streams. Now, the Hermes streams were actually discovered back in 1999 by Amina Hermes and collaborators by using Hipparco stars, and they discovered the streams as two substructures in the velocity space located at specular vertical velocity. Now, the way you should interpret this stream is the following. So some of the stars of the stream crosses the disk with positive vertical velocity, then they wrap around the Milky Way and go down with negative vertical velocity on the other side. So this is basically a stream that wraps around the Milky Way, okay? And then, of course, thanks to the Gaia second data release, the number of members increased, and therefore we could try to reconstruct the fundamental properties of the progenitor of the Hermes streams. Now, let's start by the chemistry to say that the metalistic distribution of the Hermes stream stars peaks at about minus 1.7, so it is rather metal poor, and it shows a significant spread in metallicity. Moreover, if we look at the color magnitude diagram, the age of the members is consistent with being old, and will also show in a spread of 1 or 2 giga years here. But while old ages, metal poor metallicity distribution, and spread in age and metallicity are features that are typical of dwarf galaxies. So indeed, we believe that the progenitor of the Hermes stream was a dwarf galaxy, but how massive and when was it accreted? So in order to estimate the stellar mass of the progenitor, we compared the velocity dispersion of the members of the Hermes stream with a simulation of the stream itself. So we performed different simulations, every time assuming different stellar mass for the progenitor of the Hermes streams. And as you can see, the best match is with a progenitor of about 10 to the 8 solar masses. So this is smaller than Gaia Enceladus. And in terms of accretion time, so the Hermes streams provide a rather unique way to determine the accretion time, because the ratio between the number of stars in the positive vertical velocity feature and the number of stars in the negative vertical velocity feature depends on the number of wraps around the Milky Way, meaning that it depends on the time. And in fact, by using this ratio, we determine the accretion time to be in the range between 5 and 8 years ago. So later than Gaia Enceladus, and this is why this was a rather minor merger event. But then again, let's move to another character, which is the Sequoia dwarf galaxy. Now, Sequoia was discovered as an overdensity in the most retrograde portion of the nearby halo that turned out to be a bit more metal poor and maybe a bit more enhanced in light elements such as magnesium and aluminium compared to Gaia Enceladus. And yet, you might recall that the location of Sequoia coincides with the location of the arch-like feature of Gaia Enceladus. So currently, it is still not possible to tell which fraction of Sequoia stars actually belong to Gaia Enceladus. And the reason is that not even chemistry helps. The reason is the following. So here you see the simulations with the arch-like structure that is basically made up of these cyan stars and the green stars. So as you can see, these stars are the first that are lost by Gaia Enceladus. And as such, they are those in the outskirts of Gaia Enceladus. But if Gaia Enceladus showed the typical metalistic gradient that is shown in currently existing dwarf galaxy, then these stars will be more metal poor, as it is observed. So this is why it is difficult to break this degeneration. And yet, based on what we know about Sequoia, the stellar mass is of some 10 to the 7 solar masses, and the accretion time is between 9 and 11 years ago. So also Sequoia was minor compared to Gaia Enceladus. And then finally, another character is Thumbnas. So we discovered Thumbnas in the chemodynamical space. So we looked for overdensities in the integral motion space by also including the information on metallicity. We were able to recover Sequoia, Gaia Enceladus, the IME streams, and we found other two overdensities here that we named Thumbnas. Now, based on the available information, which is very little, unfortunately, we cannot tell whether the two overdensities share the same progenitor or not, and we can't tell much about the progenitor. The only way that it is reasonable to conclude is that due to the low energy of this structure, this merger event is supposedly very ancient, but we can't tell much more than that. Okay, so at this point, I've shown you an entire population of dwarf galaxies that are now completely dissolved within the Milky Way Halo, but then move on rather eccentric orbits. So now it makes sense to go back to the original question and ask about the dynamical link between the population of globular clusters and the population of this disrupted dwarf galaxy. Now, how can we look for this link? Well, we are going to use the integral motion space again. And what we will try to do is to associate to each of the galactic globular cluster its former progenitor. Now, to do so, we won't only use energy and vertical angular momentum, but also the angular momentum perpendicular to the vertical one, which is not actually an integral of motion, but it has been demonstrated to be helpful in recognizing overdensities in this dynamical space. All right, so let's start. The first progenitor is the most important, the Milky Way. So which among the Milky Way globular clusters actually formed in situ in the Milky Way? So we defined Milky Way globular clusters, all of those that were moving along disk-like orbits, meaning with a maximum vertical height of 5 kiloparsec and a circularity larger than 0.5. And we defined as in situ globular cluster bulge globular clusters. Now, bulge globular clusters are those within this upper limit in energy. What does this mean? So as I said before, energy goes as the apocenter. So an upper limit in energy means an upper limit in apocenter. And this means that we are selecting bulges that are confined within, globular clusters that are confined within the bulge during their orbits, okay? So, and based on this, it turns out that less than half of the population of the globular cluster formed in the Milky Way. So this was a bit surprising at the time, but based on the most recent simulation of globular cluster formation, it turns out that such a fraction is in fair agreement with the expectation for the in situ population of this kind of large galaxies, like the Milky Way. And now let's focus on the accreted population of globular clusters. So first of all, we tried to find a link between the globular cluster and the most obvious of the merger event, which is the one currently ongoing with the Sagittarius dwarf product. Now, to do so, we started from a work by Son and collaborators that determined the proper motions for a bunch of very far away globular clusters and found out that 5 of these had an orbit that was completely consistent with that of Sagittarius itself. So you can see the 5 globular clusters here with this starry symbol, but we immediately realized that others shared very similar orbital properties with this. And so we ended up with these 8 globular clusters associated to Sagittarius, and it was nice to see that our associations were later confirmed by many other studies, such as the one by Bellazzini and collaborators 2020, that confirmed all of our association except for one. And then let's move to Gaia Enceladus. So how can we associate a globular cluster to Gaia Enceladus? Well, we did so by comparing the location of the globular cluster in the integral motion space with the location of the stellar debris of Gaia Enceladus in the integral motion space. So this is where the stellar debris is located, and therefore these are the Gaia Enceladus globular clusters. Let me also highlight these two here that might be located along the arch-like feature. And then we played the same game, basically with the hemistreams. So here in green, maybe you can see the stellar members of the hemistreams. And here in yellow are the associated globular clusters. And then with Sequoia. And these are the associated globular clusters. Again, these two are consistent with being associated to both Sequoia and Gaia Enceladus. Now, Thumbnas has no associated globular cluster. It would be located about here, and this might tell us something about the mass of Thumbnas. Very likely it was too small to host a system of globular clusters. But at this point, we have associated the globular clusters to all of the known progenitors, so old mergers of the Milky Way. And yet, we are left with some globular clusters that are still unassociated. So some are located up here at high energies, but others in black are clustered here. So let's focus on these. So this is a group of low energy globular clusters. They are about 25, but they're very much clustered together. And as I said before, clustering in the integral motion space very likely means similar origin. So in fact, we believe that we have observationally discovered a merger event that at the time was unknown, but that was predicted by Krausen and collaborators 2019 based on the age metalistic relation of the globular clusters. So this effectively is the first time that a merger event has been discovered by using globular clusters, and the confirmation of this came later on from Orta and collaborators 2021. They basically found the stellar debris of this merger event that was called Kraken. So here you see Orta and collaborators focused on inner halo stars that share the same orbital properties as the globular clusters of the Kraken. And by looking at their chemistry, they found out that some of these stars have a chemistry that is completely consistent with that of an accreted population. So in terms of fundamental properties, Kraken has a very low energy, and this very likely means an early accretion, and purely based on the number of globular clusters. So this estimate for the stellar mass might not be extremely precise, but based on the number of globular clusters, it shares a similar mass compared to that of Gaia Enceladus. But this means that Kraken was also a very important character in the assembly tail of the Milky Way. All right, and finally, we were left with about 11 globular clusters that you see in cyan, unassociated, but as you can see, their distribution is not coherent at all in this dynamical space. So very likely, this means that this cluster were not accreted from the same progenitor, but most likely from several small progenitors that brought in a few globular clusters that are still unknown. So I think this was pretty exciting when we found this out, because it shows that globular clusters are very efficient in trying to reconstruct the complete assembly history of the Milky Way, especially where stars are not able to go in far away regions or in the inner halo, where the extinction plays a very important role. And other than the dynamical information, I would also like to discuss the information that we have on age, because you see here, the green lines are theoretical age metallicity relations whose shape basically depends on the mass of the progenitor. So we took the various estimates for the mass of the progenitor that I mentioned, we drew the theoretical models and we tried to see which were the age metallicity relations of the globular clusters that we associated using the dynamics. And you see that they very nicely follow the theoretical age metallicity relation. So this was also very nice to see, because this demonstrates that age is another very important information that would be very important to use. And well, at this point, I would conclude my first part of the presentation with the table that basically associates to each galactic globular cluster its former progenitor. But at this point, you will have already realized that some of these associations are clearly uncertain. And the reason is that in the dynamical space, the debris of the different progenitors sometimes overlap. And when they do so, it is very difficult to tell whether one cluster belongs to one or the other progenitor. Now, the only way to break these uncertain cases would be to include further information. This further information could be the chemistry, could be the age information. Of course, it could be improved kinematics. And what we are going to do in the future is to focus on the age information. And we will going to do so with a team of people that also involves Santi and Adriano here in Teramo, according to this KARMA project. Basically, the aim of the project is to determine the age metallicity relation for the entire population of globular clusters. Now, this is rather challenging. We are going to do so by collecting homogeneous photometry for the largest sample possible of globular clusters, possibly in BVI bands. And of course, we are going to use the most up-to-date theoretical models to try to determine the relative ages of the globular clusters. But of course, it will take time. So I won't talk more about this, but please stay tuned, because I think that very exciting results will come out of this in due time. And at this point, I would move to the second part of my presentation that is very much connected to the first part, because I would like to discuss the assembly history of an external galaxy. So not anymore the Milky Way, but one of its satellites. So actually the most massive of the Milky Way satellites, which is the Large Magellanic Cloud. Now, can we try to investigate the assembly history of the Magellanic Cloud? Well, the LMC is very far away. So as I said before, stars might not be the best tracers now with the information that we have to investigate this kind of system. So let's not use stars, let's use globular clusters again. And what information can we use about the star clusters of the NMC? Can we use dynamics? Unfortunately, we can't. And the reason is that the NMC is too far away and too crowded for Gaia to provide precise and accurate proper motions enough to try to reconstruct the dynamics of the system. So currently, the only stellar cluster for which an accurate estimate of the proper motion exists is NGC 419, for which we determine the proper motion by exploiting 3 epochs of HST data that were very much separated in time. So this is actually one of the few cases where HST can still beat Gaia. And you see here that we managed to do so. So this is the column-height diagram of NGC 419. This is the proper motion space. And you see that we can very clearly kinematically distinguish the stars belonging to the star cluster in red from the main population of the LMC that you see here in blue, and from a third population that we found out that turned out to be linked to the so-called Magellanic Bridge. But well, this is to say that no, we can't use dynamics. So can we use age? No, we can't. We don't have the data that are good enough to get precise age information to do so. But then we can use one of the properties that I have not discussed yet, which is the chemistry. So in fact, we investigated 11 old LMC star clusters, and we determined with an extremely high accuracy, which is key for this kind of study, the elemental abundances for 13 species. So you see here the results for 2 alpha elements, silicon and calcium. So in gray, you see Milky Way globular clusters. And in green, you see our 11 old NMC clusters. Now, especially in calcium, you see that they seem to be underabundant compared to the Milky Way globular cluster. But this is fully to be expected because this cluster formed in an environment that formed its stars with a lower star formation rate, and therefore their alpha enhancement is smaller compared to that of the Milky Way. And yet, among the NMC cluster, one, NGC 2005, seemed to be even more underabundant. And it turns out that this is true not only in terms of alpha elements, but in terms of any of the 13 species that we investigate. So in this plot, you see in red NGC 2005, and in green, the mean abundance of the star cluster located at its metallicity. Now, we try to explain such a peculiar chemistry by means of the most up-to-date chemical evolutionary models. And the only way we found in order to explain such a chemical behavior was to assume that the environment that formed 2005 formed its stars with a star formation rate that is even lower compared to that of the LMC. But which kind of system can do so? Well, a dwarf galaxy that very likely orbited the LMC and then was accreted by the LMC itself. Ultimately, Lambda CDM is self-similar, so even the satellites of large galaxies might have their population of satellites. And we believe that we have found the first evidence of one of these satellites for the LMC that was accreted and that left as a debris NGC 2005. So we also try to reconstruct some information on the stellar mass of the progenitor. Now, of course, the most natural comparison we could do was with the dwarf galaxies that currently orbit the Milky Way. And therefore, we compared the chemistry of 2005 with that of some of these dwarf galaxies, such as Draco, Ursa Minor, and Phoenix. And you see that overall, there is a fair agreement between these two systems, these systems. So we expect the progenitor of 2005 to have had a mass similar possibly to that of Phoenix, which is a dwarf galaxy that hosts a system of globular clusters, but we can't say much more than that, unfortunately, yet. And at this point, well, I will go to my conclusions. So I hope that I have clearly shown that Gaia has finally opened the possibility to reconstruct the complete assembly history of the Milky Way. But in order to achieve such a completeness, we can't rely on stars only. We need to use other tracers. And I think that the best tracers to do so are globular clusters, because this allows us to investigate faraway regions and regions hidden in the inner area. And I hope to have convinced you that globular clusters are actually very efficient in doing so, because, for example, they allowed us to discover a merger event, Kraken, and not only to do so in the Milky Way, but even in external galaxies. And we have given a demonstration about this on the nearby NMC. But with the advent of the future instrumentation, we will be able to investigate the globular cluster system of faraway galaxies. So I think that in this sense, the future is bright. But for now, I will stop here, and I thank you very much for your attention.
Okay. Many thanks, Davide, for this very interesting